Hello everyone. Today we are going to look at section 4.2, which is all about weight. Our learning targets today are to be able to identify the difference between mass and weight and to explain how the value of G is different on different planets. And our essential learnings are how are weight and mass of an object related and how does G change on different planets. So let's start with a little bit of review. You know that's what I like to do. We are going to focus on Newton's second law today, so we need to remember that Newton's second law tells us F net is equal to mass times acceleration, or, of course, you can write it as acceleration is net force divided by the mass. Okay, and we also need to remember what mass is. So mass is the amount of molecules in an object. Okay? Now this is new. Weight. Weight is the effect of gravity pulling on an object's mass. In other words, the more mass you have, the more weight there will be. Okay, so the bigger something is, generally, the more it weighs. There are a few differences, but we're gonna go with the more massive something is, the more it's going to weigh. Okay, so we also need to know what acceleration due to gravity is on Earth, because we know that in order for to think about a force, we have to have an acceleration. So remember that acceleration due to gravity on the Earth is 9.8 meters per second squared. Now when we're talking about weight, we're going to call that G. In other words, this value, acceleration due to gravity on Earth, has a very special variable that we don't use for anything else, and the variable that we're going to use is this lowercase g. So anytime you see G, you're going to know that that means acceleration due to gravity on the Earth. That erased more than I wanted it to. There we go. Okay, so in order to calculate weight, and we're going to say that weight is Fg, right? The force of gravity acting on an object, so that's weight. We are going to multiply the mass, which we know is m, times acceleration due to gravity, which we know is g. So the formula looks like this. Fg, the force of gravity, which is the same thing as the weight, is equal to mass times the acceleration due to gravity. Or, of course, you could write it as acceleration due to gravity is equal to the weight divided by the mass. Now, the only thing we've done is we have changed net force into gravitational force, but otherwise this is the same thing as Newton's second law. All right, so stop the video for just a minute. Take a second, make sure that you understand all the connections there. All right, and when you're ready, we can go on and do the first example. All right, let's look at example number 1. So example number 1 says an average Maine Coon cat, I forgot I needed the highlighter, has a mass of 5.9 kilograms, it's about 13 pounds. Okay, so that's an important piece of information. What is the weight, so that's what we're looking for, of the cat in newtons on the Earth? Now, the Earth, this is important as well because that tells us something about the acceleration. So let's go ahead and write down what we know. The mass of this cat is 5.9 kilograms. The acceleration due to gravity is going to be 9.8 meters per second squared because we're on the Earth. And we are looking for the weight, so Fg. By the way, did you know that Maine Coon cats are the largest domesticated species of cat? It's true. So here's our formula. The weight right, which is Fg is equal to mass times acceleration due to gravity. So if I fill in what I know, I've got 5.9 times 9.8. Where'd that 9.8 come from? That's acceleration due to gravity on the Earth. So the weight of this cat on the Earth is going to be 58 newtons. All right, which is a good-sized cat, huh? Yeah. All right, so far so good? Okay. So what happens if you're not on the Earth? So we also know that acceleration can change if we leave the Earth. For example, if you were to go to Mars, acceleration due to gravity on Mars is 3.5 meters per second squared because Mars is smaller than Earth. So the smaller a planet is, the less acceleration due to gravity it has. Mars is about 1/3 the size of Earth, so the acceleration due to gravity on Mars is about 1/3 the size it is on Earth. All right, so let's take a look at example number 2 here, and it says, use the mass of the cat above to calculate the weight on Mars. Okay. Now this problem doesn't have any numbers in it, does it? Isn't that strange? But that's okay because we already know what most of them are. So the mass of the cat is still going to be 5.9 kilograms. Acceleration due to gravity this time, because we're on Mars, is 3.5 meters per second squared. And we are still looking for the weight. So here's my formula. Weight is equal to mass times acceleration due to gravity. I am going to plug in my 5.9 because the cat hasn't changed, and my new acceleration due to gravity, and that means that the new the new weight of this cat on Mars is 21 newtons. Now, the cat didn't change, right? It's the same cat on Earth and on Mars, but the weight of the cat is different because acceleration due to gravity changed. Okay, so hang on to that thought. That's going to be important. So again, why don't you pause the video, make sure you feel comfortable with all of this, how to solve the problems, and why we use 2 different numbers for acceleration due to gravity. And when you're ready, we can go on. Okay. So we can also work backwards to find acceleration due to gravity, right? And so that's what we would do if we were going to use the other version of this equation. So acceleration due to gravity is equal to the weight divided by the mass. So remember, let's just put it off here in the parentheses. This is the weight, and this is the mass. All right, so if I know the weight and the mass, I can find the acceleration due to gravity. So let's do that. Next problem. Same cat from problem 1. That's important, right? Because it tells me the mass. So the same cat from problem 1 is now on the moon, and it weighs 10 newtons. And we want to know what the acceleration due to gravity is on the moon. So here's what we know. The mass of the cat is still 5.9 kilograms. The acceleration due to gravity on the moon is what I don't know, but I do know that the cat weighs 10 newtons. Now, that's one of those things that might trip you up later. When they talk about weighing or weight or anything like that, it's always going to be a force. So we're always going to call it newtons. So here's my formula. Acceleration due to gravity is the weight divided by the mass. So I've got 10 newtons divided by 5.9 kilograms. So that means acceleration due to gravity on the moon is about 1.7 meters per second squared. So that's really small, huh? Does that make sense? It does. The moon is quite a bit smaller than the Earth, and so it makes perfect sense for the acceleration due to gravity to be very small. All right, last thought for today. The weight of an object can change because acceleration due to gravity changes, but mass always remains constant. All right, let's say that one more time. The weight of something can change, but the mass is always going to remain constant. All right, so you have 2 problems to work on here. And when you come to class next time, we'll turn these in. If you have any questions, make sure that you jot them down in your notes so that you remember to ask, all right? And let's take a quick look back and make sure, can you identify the difference between mass and weight? And can you tell me why G changes on different planets? Okay, and I will see you next time. Thank you so much.